Good morning, lecturer. This is our group video presentation for the group report of system modeling and simulation. Our topic is group level system with the mechanical component. This video presentation is prepared by Yubin, Sophie, Faiz, and Shiro.
Assalamualaikum. My name is Muhammad Faiz bin Hussein and my metric number is CD22008. And I will present about my part of the project, which is about a fluid level system with a mechanical components. The specific case study is a two-tank fluid level system with a mechanical valve. This system focuses on how the water flows from another tank to another and how the valve affect the water level response. In this presentation, I will explain about the background of the system, the problem statement and objectives, the physical system description, the simulation methodology, and the mathematical model used for the verification. Fluid level control systems are widely used in many industries. For example, they are used in manufacturing, chemical processing, water treatment, and beverage productions. In these industries, maintaining the correct liquid level is very important because it helps to ensure safety, product quality, and continuous operations. For this project, we use a two-tank system because it is a good example for system modeling. This is called coupled dynamics, where one part of the system influences another part. Because of this interaction, the system is more realistic compared to a simple single tank model. The main problem in this project is that a single tank model cannot accurately represent the real behavior of the system. This is because the two tanks are connected and the flow between them depends on the level difference and the valve resistance. So, the system must be modeled as a coupled second order system. This allows us to predict both the transition response and the steady state response more accurately. The objective of this project are first, to introduce and to analyze the basic components of the two tank systems. Second, to derive the governing differential equation using conservation of mass. Third, to implement the mathematical models using MATLAB and Simuli. Fourth, to verify the model by comparing it with theoretical steady state values. Lastly, to investigate the effect of the valve resistance, tank size, and inflow rate. This slide shows the physical system of the two tanks model. The system has two main storage elements, which are tank 1 and tank 2. Tank 1 has cross-section area A1 and water level H1. Tank 2 has cross-sectional area A2 and water level H2. Water enters tank 1 through the inlet flow, which is labeled as Q in. Then the water flows from tank 1 and tank 2 through the mechanical valve. This flow called Q12. The valve between the tanks is represented by the hydraulic resistance R12. If the resistance is low, the valve is more open and the water can flow more easily. If the resistance is high, the valve is more closed and the flow is restricted. Finally, water leaves tank 2 through outlet flow, which is labeled as Q out, and the outlet resistance is represented by R2. The slide shows the methodology used in this project. The first step is to define the system, while the second step is to state the assumptions. The step is to derive the equations. The fourth step is to build the model in MATLAB or Simulink. And the fifth step is to run parameter variation study. And the final step is verifications. Mathematical model and verification strategy. So our group uses governing equation. There are two governing equations that we use, which is flow equations, and the second one is state variable second order system. And the verification checklist simulation runs until dh over dt is equal to 0, and simulated output h1 h2 completely reach the mesh theoretical values.
My name is Yubin. My contribution in this report is solve the MnS simulation and also the Simulink simulation. So now I will explain about the simulation part. And this is the baseline parameter of our group using the tank 1 area is 0.04, tank 2 area is 0.04, and the inlet flow rate is 0.001, and the ref resistance between tank is 1000, and the outlet resistance is 1500, and the time step to solve the simulation is set as 1500. In MATLAB, I define all the parameter of the system, and then also the variable h and also flow equation. And also I solve two differential equation based on the mass balance equation. The first equation is to represent the change of the water level in tank 1, where the inlet flow enter tank 1 and the inter tank flow leave tank 1. The second equation is represent to the tank 2, where the inter tank flow enter tank 2 and the outlet flow leave tank 2. So here is the result of the MATLAB coding run. The graph is show the steady state of H1. The blue line is 2.5 and the orange line is H2 is the steady state is 1.5. From the command window, the theoretical H1 is 1.5 and the simulate H1 is 2.4998, and the theoretical H2 is 1.5 and the simulate H2 is 1.5002, and both of the percentage error between theoretical and simulate value is very low below than 0.02, so we is verified. So this is the overall Simulink plot diagram, and the sun plot is represent the H1, H2, and the grand plot is represent to 1 over resistance 1, 2, and 1 over resistance 2, and 1 over area of tank 1, and also 1 over to area of tank 2. The integrator plot is to obtain the H1 follow the time and also H2. The scope and to workplace plot is record the water level response. So now I explain about the MATLAB and Simulink simulation. So this is our baseline coding in MATLAB, and this is the parameter I define in this system, which is A1 tank 1 area, A2 tank 2 area, Q in inlet flow rate, R12 wave resistance between tank 1 and tank 2, and also R2 outlet resistance. And this is the equation I use in this to run the simulation. And this is the full coding for my MATLAB. So now I run the simulation. From the command window, we saw that the theoretical H1 water level is 2.5 meter and the simulated H2 final value is 2.4998 meter. The percentage error between the theoretical and simulated H1 value is 0.097, and the H2 theoretical value is 1.5, and the simulated H2 value is 1.5002 meter, and the percentage between theoretical and simulated H2 value is 0.013. So the both percentage error is below than 0.02, so which is verified. So we see the graph for the baseline response of two tank flow levels system. So we can see the H1 is graph to 0.2, sorry, 2.5, and the H2 is go to 1.5, then become steady state. After that, we go to the simulate flow diagram. So this is the overall simulate flow diagram of baseline, and the Q1 is for inlet flow rate, and this the sum is for Q1. This is the sum for H2. Sorry, this is the sum for H1, and this is the gain for H1, gain for H2, integrator for H1, and integrator for H2. And this is the display to display the water value of H1. This is the for H2. And the product again all come from this library poster. And the interest time step I set is 1500. So now we run the simulation. So we can see the output of H1 is 2.5 and the output of H2 is 1.5. So which match to the theoretical value. So this table show all the tests we simulate in this project. The first case is baseline. We use the default parameter set as a original case, and the case 2 is we change the resistor 12 to 500, and the case 3 is we change the resistor 12 to 2000, and the case 4 is we change the area of tank 2 to 0.08, and the last case, case 5 is we change the inner flow rate to 0.0015.
For the result of the study, developed MATLAB model was verified to ensure that the simulation accurately represents the behavior of the two tank fluid level system. Model verification was performed by comparing the theoretical steady state values with the simulation result obtained. What we get is error less than 0.02%. Excellent agreement between theory and simulation. Model successfully validated for the further analysis. For the baseline case, tank 1 final level obtained is 2.4998 meter and tank 2 obtained final level is 1.5002. The system reached steady state successfully. Inflow and outflow are balanced. Use a reference case for comparison. Next, effect of valve resistance. For the case 2, valve more open which R equal to 500. The result obtained is H equal 1.9998 meter, H2 equal to 1.5002 meter. For the observation, faster response, lower tank 1 water level, easier flow between tanks. Next is case 3, valve more close. The results obtained is H1 is 3.5994 meter, H2 is 1.5998 meter. For the observation obtained is higher tank 1 water level, more water accumulated in tank 1. Flow between tanks are restricted. Then the conclusion we get is valve resistance significantly affects water distribution. Higher resistance causes greater level difference. Lastly, the effect of tank size and inflow rate. Larger tank 2, area equal to 0.08 meter squared. For the observation, we get is slower transient response. Steady state level remain unchanged. Larger tank stores more volume before reaching equilibrium. Next is higher inflow rate. Q in equal to 0.005005 meter cube per second. For the observation, both tank levels increase. Longer settling process. Higher flow required to be balanced outlet.
Good morning. My name is Siroshan Prabhu. My metric card number is CD220193. So I'll be discussing the discussion part of this report. So next, I will discuss the findings obtained from the simulation study. First is model verification. Before conducting the parameter analysis, the MATLAB and Simulink model was verified by comparing the simulation results with the theoretical steady-state values. From the result, the percentage error for both tank 1 and tank 2 remained below 0.02%. This shows excellent agreement between theory and also simulation. In addition, the flow balance condition was achieved where the inlet flow between tanks and also the outlet flow reach approximately equal values at steady state. Therefore, the developed model can be considered accurate and also suitable for further investigation. Next is effect of valve resistance. For the valve more open condition where R12 equals to 500, water transferred more easily between the tanks. As a result, tank 1 reached a lower water level and also system stabilized faster. However, the valve became more closed in with R12 equal to 2000. Water transfer became restricted and more water accumulated in tank 1, producing a higher final water level. This shows the valve resistance plays an important role in controlling fluid distribution and also response characteristics of the system. Thank you. Next, we analyze the effect of tank size and inflow rate. For the larger tank 2 configuration, the steady-state water levels remain almost unchanged compared to the baseline case. However, the response became slower because a larger tank requires a greater amount of water before the level changes significantly. This means tank size mainly affects the response speed rather than the final operating condition. For the higher inflow case, increasing the inlet flow caused both tank 1 and tank 2 to reach higher final water levels. The system also required a longer time to stabilize because more incoming fluid needed to be balanced by the outlet flow. Overall, these results demonstrate that the tank size influences transition behavior, valve resistance control, water transfer, and also inflow rate has the greatest effect on the final operating levels. In conclusion, this project successfully developed a mathematical model of two-tank fluid level system using the conservation of mass principle and implemented it using MATLAB and Simulink. The verification process showed excellent agreement between theoretical and simulation results with an error below 0.02%. From the parameter investigation, lower valve resistance improved fluid transfer, larger tank size slowed the system response, and also higher inflow significantly increased the final water levels. Overall, this project demonstrates how mathematical modeling and also simulation can be used to predict the system behavior efficiently before practical implementation. Thank you.